Thank you. Thank you, Andreas, for the long and great introduction. Blockchain technology is great, but it comes with unprecedented security challenges, mainly because of potential bugs that can exist in software, which can have catastrophic effects. So let's try to get into the mood for the presentation by showing you a bit the flow of execution in a blockchain. So let's start with, and I typically have in mind when I say blockchain, I think the Ethereum style blockchain, where you can write arbitrary programs to perform transactions. So for the purpose of this talk, let's think of transactions as arbitrary code, which is given, which is public, so everybody can see and can invoke. And the code operates on a large shared state. Then there are all the nodes that have to basically validate transactions, and they do so by re-executing all the code, and they have to operate using agreed upon virtual machines or execution environments to make sure they get exactly the same results. Then once they validate the transactions, they group them in blocks, and then they append them to the block, as we know. But what's important here is that some transactions can actually contain code, and this way we can actually have code on the blockchain, which we call smart contracts, and that code can be invoked by other transactions. So anybody can put code on the blockchain, and anybody else can invoke that code. And in the end, all the code is public, can be invoked by everybody, as I said, and it can irreversibly change the history. And obviously, that, as we know, that creates huge incentives for hackers to attack the code, and specifically to exploit bugs or unexpected behaviors of these smart contracts. And this is, I keep saying that I want to reemphasize that this is giving us really a context that we have not seen before, where all the code is public, and anybody can attack it. Of course, we need safety-critical software in cars, in airplanes, and that code also can be attacked, but most of the time, if you want to attack that code, it's like shooting in the dark, because you don't know exactly the code. You can, not even Toyota knows the code that runs in Toyota cars, for example, but now you see the code, and you know how to attack. You can schedule an attack. So the bottom line is that it's important to have correct programs and correct virtual machines that execute these programs. And programs look like almost any other programs that we are familiar with. Like, for example, this is part of an ERC20 contract in Solidity, where we have a transfer function. You transfer to a certain address, a certain value, and you do pretty much usual stuff. You check if the value is 0, return false. Otherwise, you check if you have enough funds. Check if you can perform an overflow at the target account. And then if everything is OK, do the transaction, meaning that you subtract the value from your account, add it to the other account, and then you log information. So it may look very innocent, but actually even this code, as simple as it is not compliant to the ERC20 protocol. Specifically, the ERC20 doesn't state that if the value is 0, you should return false. It says that you should still perform and log the transaction. Actually, others may rely on that. Then also, there is a special case here that you may not think about up front, which is when you transfer to yourself. If you transfer to yourself, you don't have an overflow. It's a special case to the rule. It's not necessarily critical, but the point is that this does not satisfy the specification of ERC20. Nothing critical here, but there have been critical attacks. As you may remember, the beauty coin attack, where something similar happened. So in this particular variant of ERC20, you have a batch transfer function, where you take an array of receivers, and you transfer a certain value to all of them. And the way it works is that you count how many you have, and you calculate the amount that you have to subtract. And then if you have enough, and some other conditions are satisfied, then you subtract that amount from your balance, and then you distribute it to all the receivers. So there is a huge problem here, and it was not noticed until it was exploited, which is, anybody knows what the problem is here? Overflow. So this multiplication can create an overflow, And if this overflows, if the counter is large enough and the value is large enough, then you create an overflow, and then the amount will become a negative number, a huge negative number, right? And when you have a huge negative number, amount, obviously your balance is larger than that. And then when you subtract the huge negative number from your balance, what happens? You actually add a huge positive number to your balance, right? And that's exactly what happened. And then you also give a little money to the rest of the receivers, but the point here is that this overflow created you a lot of money. And indeed, that attack actually happened, and it led to the creation of coins in the value of 10 to the power 70, right? So it's not like, you know, you steal $1 million anymore, right? So you literally can completely destroy a business with an attack because of a bug. One little bug in the program can lead to the end of an entire business. And this is just one more recent attack, but there are many others, as you know, that made the news, where hundreds of millions were frozen or lost. And I don't want to insist on those. I just want to show you that, hopefully to convince you that bugs are a serious issue and they can be exploited and they can have catastrophic consequences. And then the question that we can ask as programming language or formal methods people, like I am, is what can we do about it, right? There are lots of things that can be done, maybe at economical scale or other social scales where I cannot have an opinion, or I can have but nobody cares. But in terms of programming languages, what can we do to make sure that programs execute as they are supposed to execute? How can we make sure that programs do what they are supposed to do? And in particular, I strongly believe that we are in a very happy, fortunate situation where the ideal scenario that has been the holy grail of the programming language and formal methods community for many, many years, I think that is finally possible. We can make that happen in the context of the blockchain. And I hope I can convince you that at least it's worth a try. Let me, specifically, I believe that everything can be completely rigorous and completely provably correct. In nodes where we run virtual machines, those should be provably correct, because if the virtual machines have bugs in them, then they can disagree on what programs are supposed to do. So you just don't want to have that. So virtual machines or interpreters that run the code, they can be provably correct. Then contracts should be written in well-designed programming languages with provably correct compilers, so you take no chances because of bugs, unexpected bugs here or there. And then in the end, that whatever smart contracts we have, that we can formally verify them and make sure that the exact code that runs actually satisfies the desired properties. Let me tell you a few words about what I mean by an ideal language framework. What do I mean by things being ideal? So many programming language fundamentalists believed for many years, and I'm one of them, some of them believe very firmly in that, and I'm one of them, that we can have a formal language definition of a programming language. That means both syntax and semantics. And then we can derive from that automatically or semi-automatically all the tools for that language. Okay, we're already doing that with parsers. We have parsing frameworks where we specify a syntax of a programming language, like an LR or LL grammar, and then we generate parsers. Right, but let's go further. Let's have the entire language, not only syntax, but also semantics, and they generate all the tools automatically from the formal semantics. So that's the vision, and that includes not only interpreters or parsers, but also compilers, debuggers, semantic debuggers, symbolic execution engines, model checkers, and ultimately program verifiers, deductive program verifiers that allow you to prove basically any property about any program in any programming language, in such a framework. And that is possible. It's not a dream. Before I go more deeply into the ideal approach, let me first remind you what the state of the art is in our field. So on the one hand, we have languages. On the other hand, we have tools for such languages. And then we see all kinds of combinations between these, right? One of the most common tools is a compiler for C, for example, GCC. Right? You compile GCC programs into something else and then execute them more efficiently. But this is not the only tool that we have for C. There are also interpreters for C, like the dynamic analysis tools, for example, for C, that observe many things in check for undefined behaviors and so on in C programs. Then we have also model checkers for C. Then we have also symbolic execution engines. We have deductive verifiers like VCC, for example. And essentially, all these tools for C are developed by different teams, and they reuse almost no code across the different tools. And they have many parts which are common, but still they're developed completely independently. And then we do the same for other languages, for Java, for example. And a model checker for Java is not that different conceptually from a model checker for C. Yet there are different people, different time frames implementing the same algorithms, conceptually the same algorithms, over and over and over again for each language. And then now we see the same thing in the Ethereum framework setting, right? Or blockchain. We see Solidity tools, starting to appear for Solidity, for EVM, and the same idea, the same somehow uneconomical approach where we, as a community, re-implement the same techniques over and over again in the context of a different language. So just a slightly different face to the same main problem. We believe that we can do better than that. And this is what the ideal language framework promises, is that you can have actually all the tools, all these blue boxes incorporated in a framework that is parameterized by the language. Right? So you have a language that is passed to the framework, and then all the tools only care about that parameter. So the tools are developed in a parametric way, okay? As opposed to implementing a model checker for C. There is no such concept in an ideal framework. In an ideal framework, you have a model checker, okay? And now the language will be passed as input, right, to the framework. And indeed, then we can separate concerns and define all the languages through their syntax and semantics, and then pass those definitions to the framework and get all the tools for the languages. So instead of having L times T, where L is the number of languages and T the number of tools, so instead of having L times T systems that we have to worry about and maintain and all that, we have only L plus T, right, if everything goes as expected. So I'm not saying that we have solved the problem of the ideal language framework. All I'm saying that what we have tried to do for almost 20 years now is to try to achieve a framework like that. So the entire K framework that I'm going to talk about has been designed from the very beginning with that vision in mind. I've been teaching programming languages since forever, since I can remember. And since I believed in this ideal framework approach, I searched for such a framework for many, many years. In particular, when I taught programming languages to different generations of students, I tried to see which of the existing semantic approaches seemed to be the most appropriate. And I literally went through more than 15, I would say, different semantic approaches. I listed some of them here. But then it turned out that each time you try to design a language or to define the semantics of a language, which was a bit more complex than a toyish academic style language, you run into issues, especially with modularity, with extending the language, adding a new language a new feature to a language, forces you to go back and change everything in your definition. So very demotivating aspects of the frameworks that I think are part of the reason why we do not have formal semantics to lots of languages out there, simply because all these hassles demotivate people to do that. So what we really tried to do was to literally engineer a framework that would avoid all the limitations of the various approaches that have been in different uses in different frameworks, and at the same time to avoid the limitations and to keep all the advantages that they had. And once that turned out to work, then we sat down and came up with the theory, as opposed to developing the theory first, and now let's try to implement something that fits the theory. That was not what we did. So what we did was to first implement it, make it work, define several languages in it, and then we developed the theory. And most likely I will skip the theory, because I may not have time to talk about it. Let me give you flavor of what we experience as a user of K when we define a language, let me show you just some snapshots of language definition, a language which we call kernel C, a fragment of C that we use in some projects. So what you have here is what we call the language poster, which is generated automatically. One of the tools generates such documentation from your definition. So what we have here, we have basically syntax to the left and some macros that expand the syntax, and then semantics to write the other two columns. Syntax is defined using conventional BNF. It turned out that this is one of the most accepted notations for syntax. And we were driven a lot by user feedback. And one thing that we learned is that when you define syntax of a language, people want to define the evaluation strategies of the various language constructs right then when they define the syntax, as opposed to go somewhere else to define evaluation strategies and semantics. So semantics means the meaning of the various constructs, but the evaluation strategy is something, it's also meaning, but a very well understood meaning, and each framework has its own way to deal with evaluation strategies, and it doesn't really matter. You just want to define evaluation strategies quickly and get them out of the picture. Like, for example, plus. Plus, what's the semantics of plus between two expressions? You say, oh, I'm going to evaluate the first argument, the second argument, and then I'm going to sum the results. Okay? This evaluation of the first and the second, you don't want to spend time to write rules for that, because that's a very common operation when you define semantics. So because of that, we invented such annotations in K that allows you very quickly, as you define the syntax, to immediately define the evaluation strategies of the constructs. And that saves a lot of time. Then, when you define a semantics, you typically need a notion of a program configuration, which is some data structure that holds everything. And we learned from the chemical abstract machine and the gamma model, I told you we studied lots of different semantic approaches, that it is really nice to have this metaphorical meaning of a program configuration as a solution, as a chemical solution in which the various molecules float and they can meet and react. And then you have reaction rules that turn molecules into other molecules. Right, so anyway, so we borrowed that idea from the chemical abstract machine, and now we define configurations like this. We call these semantic cells, and we can think of this really like a wrapper around things that hold semantic information. And these things are named. Like, for example, for this language, you have a K cell which holds the program, or whatever is left of it, the continuation, we call it the continuation. Then funds holds all the functions in your program. Environment is the environment. The memory, the function stack, input-output buffers, a pointer map, because this language has malloc, and you need to know how much memory you allocate in order to free the memory. So anyway, so eventually you come up with such a configuration for your language, no matter what your language is. And then the final part are the rules, the semantic rules. And they look like this. This is what we generate in the poster, and this is how you write it in ASCII. So basically, a rule is the only computational entity in K. So everything you do with rules. And rules mention a context. You can think of rules as transactions, right? Where they match some context of the configuration they want to change or read or write. And then you grab everything you need, and then parts of what you grabbed need to be written, and you write those, right? So here, this is the semantics of assignment. Remember, assignment was strict in the second argument. So the second argument now evaluated to a value. You can assume it's a value. And what is the semantics of assignment? You say, well, I'm going to consume the assignment, x equals v evaluates to v in C, but as side effect also writes the value of x to v in the environment. All right, so that's the intuitive meaning, and this is the actual formal thing saying exactly the same thing, where you say, I'm going to grab from the code the assignment, and I'm going to rewrite it to v, and at the same time in the environment, I'm going to match x bound to whatever it is. This is an anonymous variable, and I'm going to change it to v. And this squiggy zigzag, the tears in the cells, the meaning, the metaphoric meaning there is that there is more stuff there, but you don't care about it, right? And when you write it in rules, actually you use ... So users propose that because you don't want to write things that you don't care about, right? So how can you write those ... And as you can see, actually this is like a rewrite rule, but there are two rewrite transformations. So two transitions going on in the context. So the rules in K are very contextual. You write a context, and then some parts of the context, some subterms in that context can be rewritten to something else. All right, so basically it's saying that in the code cell, if I have the assignment x equals v, I write that to v. And in the environment, I don't care what it is before or after, but I have a binding of x to something. This is the maps to. And whatever that is, writes to v. Right, so that's how you write rules. And that's it. You define syntax, then you define a configuration, and then you keep adding rules like this. And this way you can define large languages completely. So we defined lots of languages so far, we or other groups. Like JavaScript, for example, ECMAScript 5 has been defined completely, Java 1.4. We just finished the semantics of x86 completely. There are more than 3,000 instructions, all of them semantics, so now we can execute actually binaries, x86 binaries, and analyze. C, the semantics of C11 has also been completely defined. And now, more recently, we started defining semantics of blockchain languages. But for us, the fact that these languages are blockchain languages makes absolutely no difference. I know it's a blockchain conference, so I should say that blockchain is very special. Yes, it is, and it's great. But in our framework, the fact that we deal with blockchain languages is no different. And when I say that we define the semantics of these languages, I mean that we define them completely, not like we define a convenient fragment, or not even that we define 95% of the language or even 99% of the language. No, we define the languages completely to a point where we can take actually benchmarks and execute them with the tools generated automatically from these semantics. Okay? And the reason we want to have complete semantics is because we want to analyze real programs as are there. And not to reduce them to a fragment or anything like that. So one complete semantics, and then all the tools are generated automatically from these semantics. All right, now let me, so I showed you how to define things here in the yellow part, how to define languages. Now let me go a bit into the blue parts, telling you how we implement this language independent or language parametric tools. The interpreter is by far the most used tool. Actually, the parser is the most used tool, but there's really nothing really deep there. But the interpreter is the first tool that you need once you have a semantics of a language, right? Because you take programs in that language, tens of thousands if you can, every program you can put your hands on, and then run them, put them in a regression test suite, and then run them each time you modify the semantics. So the interpreter is used a lot. So currently, what we do, we generate an OCaml program from a K definition, and that OCaml program then is compiled natively, and this is how we get interpreters. Actually, in my company, we have a tool called RV-Match, which is generated from the semantics of C. So we have the semantics of C. We actually define the complete ISO C11 semantics. And from that semantics, we generate basically a product. This RV-Match tool is generated completely automatically from the C semantics. It's an interpreter for C. And what's special about it is that it captures undefined behavior. So our definition of C defines very rigorously the undefined behavior of C. And now when we run C programs or when we analyze C programs, we also check for undefined behavior, which is a big problem in embedded, for example. So this is how it works. You have a program in C. This program may look innocent. Actually, it has a problem, this program. As it happens with many programs in C with undefined behavior, when you run them with GCC, compile them with GCC and run them, you see nothing, you get something. But then you change the compiler or change options or compile it and put it on an embedded platform, you get completely different results or the program crashes. When you run it with the semantics, and this is how you run it with the semantics, just KCC. So we wrapped up the entire semantics, everything into a drop-in replacement of GCC, KCC. And we actually spent a lot of time to make it really easy to use. So the learning curve really is just one character. So if you use GCC, now all you have to do is to type KCC instead. All the options, everything are preserved. But what happens under the hood is that we run the programs with the actual formal model, for mathematical model, and we define all the undefined behaviors, and then it gives such errors to users of the tool. All right, so we already use this tool, RV-Match, in the context of safety-critical, mission-critical systems, and we have contracts with NASA, Boeing, Denso, Toyota, some of the major players in this space. And then what we do in order to apply our technology to blockchain is simply plug and play languages in the blockchain space, like EVM, EWASM now. ELA is another language that we designed. So yeah, and nothing else changes. And I'll go into more details about how we do that with blockchain languages. But first, I want to tell you a few words about some other blue boxes, specifically the deductive program verifier and symbolic execution engine, because these are critical for verification of smart contracts, right? So one of the things that we do, the main source of revenue in my company comes from verification of smart contracts, and that is done, again, into a completely language-independent way. Okay, so we use these blue boxes instantiated with the EVM semantics. So let me tell you a bit about how this works. But first, I need to remind you that the current approach, the main approach to program verification, deductive program verification, is still based on Hoare logic, where what you do is to design an entire logic specifically for your language, right? So if you want to develop, let's say, program verifier for C, then what you do, if you are very rigorous, if you are not rigorous, you just go ahead and hack something, right? And then you claim you have a verifier. But if you are very rigorous about it, what you typically do, you define a logic, a Hoare logic for your language, which will have lots of rules like this is the rule for invariants for while loops, or this is for the rule for procedures, recursive procedures. Right? So if you want to prove that a procedure has a certain pre-post condition, then you assume the procedure, and then you prove the body, and so on and so forth. So there are very specific proof rules. You have to sit down and rethink the entire language differently from this perspective. That is not language parametric. That does not work. So in spite of 50 years of research and advancements in Hoare logic, we can simply not use Hoare logic in such a framework, right? Because it is not language parametric. I want to plug and play my language. I need a Hoare logic which is generic, that I plug and play my language into it. But there is no such Hoare logic, so we need something else. So we spent a lot of time developing new foundations for program verification, where basically we have a language-independent proof system, a language-independent logic, where your programming language is the theory in that logic. And you use the same proof system, the same proof rules to do reasoning about all languages, as opposed to having proof rules specific to each language. And I certainly do not have time to go into the foundations of the logic, which I really love. But in the interest of time, I'm going to just give you high-level flavor of the logic, and then I would be glad to talk more about if you are interested or send you papers. Essentially, the logic that we came up with is the logic of patterns and pattern matching. Why? Because in this framework, in the semantic rules, it's all about matching patterns and transforming things. So you need the notion of a pattern, and what does it mean for a pattern to be matched. And then we built an entire logic based on that philosophy. And like in many other logics, first-order logics, for example, so we don't have formulae, we call them patterns, right? You have terms, some notion of term, so you build structures somehow, and we allow those. But at the same level of patterns, we also allow logical constraints, as opposed to separating them into terms and formulae, as you see in first-order logics or in other logics. Terms are one thing, you build structure with them, and constraints are something else that you build requirements from. No, we don't have such a distinction at all here. We just have patterns. And the intuition for patterns is that they are matched. So a variable is matched by everything. This is matched by any program configuration that has a sigma at the top, where a sigma is a symbol. This is matched by all program configurations that do not match phi. This is matched by all program configurations that match both this and this. And then there is also a generic binder, existential quantifier, that allows you to define all kinds of binders, including lambda binders and mu binders, certain kinds of mu binders. And all right, so that's great, but still not enough, not powerful enough to deal with induction. You definitely need induction. And to prove inductive properties, specify inductive properties, prove inductive properties. And for that, we had to extend the logic with a mu construct, a fixed point construct, and two proof rules for dealing with mu, basically capturing the Knaster-Tarski least fixed point theorem. And with that, now you have a logic which is essentially as powerful as first-order logic plus induction, but it is in a much, much more compact notation. And with that logic, you can define now as theories lots of logics that are used in program verification And at the same time, programming languages like C, Java, JavaScript, EVM, Solidity, and other languages, they are all now mathematical theories in one logic. Okay, so you have only one reasoning machinery, and you can just apply it to all languages and all logics. In particular, you can define all kinds of goodies that you have in first-order logic. You can define higher-order languages like lambda calculi. You can define model logics, Hoare logics, dynamic logics, LTL, CTL, CL star, reachability, separation logic, and what's really more important for K, now I'm getting back to K now, is reachability logic, which is the logic of K. So what is reachability logic? Reachability logic generalizes rewriting logic. So in writing logic, you have rewrite rules between terms. The left-hand side writes to the right-hand side. So here we have patterns. A pattern writes to another pattern. So this way, you can have much more complex statements than just rewrite rules. And in particular, Hoare triples, precondition, code, postcondition, can be expressed as reachability rules pretty mechanically. Right? So now we can take any Hoare logic that may already exist for a particular language and generate automatically a theory in reachability logic. And moreover, we have a theorem saying that I can take any proof in the Hoare logic specific to a language and generate a proof in reachability logic. So I can swallow everything that has been done for a specific language if I want to. But you have better ways to do things. You don't need to go that route. You can now define an actual formal semantics of the language, executable formal semantics of the language, and you can prove, if you really want to, all the Hoare logic triples as theorems, and proof rules as theorems there. Okay, I know I'm going too much into what I'm excited about, but feel free to interrupt and ask questions. I promise I'll get back to blockchain soon. All right, let me skip that. Essentially, reachability rules can be expressed now in a much more compact way once you have fixed points. So reachability is a special use, particular case of fixed points, and matching logic already has fixed points, so it's more powerful than reachability logic. And that's a very recent result, actually. We just literally proved it 2 months ago, which means that now we have a super simple and clean logic that explains everything we do in K. And let me tell you how we implemented all this in K. So what is K, really? So K is a best effort implementation of this logic, of reachability logic. And in particular, the deductive program verifier looks like any other verifier from the outside, right? You pass to it a program and some specification, a program that you want to prove some properties about. But what is really different is what happens inside the box. What happens inside the box is that there is a crystal clear separation between languages and the actual verification infrastructure, right? We use symbolic execution, where in the end you invoke SMT solvers like Z3, the usual things that happen in deductive program verifiers, except that all this part, the verification infrastructure and the theorem provers, they are completely separate from the language semantics. And people who develop these language semantics are actually literally undergrad students who don't even know about semantics, anything. They just think that they implement a language in this weird language called K. But actually they define a formal semantics that then can be used in this context. And now more recently, we just defined semantics to blockchain languages, and suddenly we can reuse everything we've done in the last 20 years in this context without changing anything, basically, just improving. And in case you are concerned with performance, we have done lots of experiments, and I can tell you that performance is not a problem. You do not pay a price for the generality. Okay, we compare to the best state-of-the-art program verifiers for C, and we are almost as efficient as them, like 5% maybe slower on some proofs, but we're also faster on other proofs. And my prediction is that this approach actually will soon be much faster than the traditional verifiers, simply because there is a lot of incentive in researchers and students and everybody to improve this infrastructure, because you simply use it with all the languages, right, as opposed to having just 2 students implement an interpreter for a language. So I showed you how you write semantics. This is how you write properties. This is a property saying that for a kernel C program, this is the kernel C program, so I guess you can read it, right? What does this program do? Right, calculates the sum of numbers up to a certain value, n. And notice that what I want to prove that this program calculates this, I want a closed form expression, right, of the sum, which is n times n plus 1 by 2. But in order to do that, I need to say that the input, this n, is a symbolic value. Right? So notice this is a pattern now. It's a pattern which contains all kind of symbols, constructs, and also variables. This n is a variable. This n is not a variable. That's a constant, actually, of sort identifier. So, and then notice that this is just a normal rule. Same like the rules that you use when you define the semantics of the programming language. So it's exactly the same logic to define my programming language, and I use exactly the same logic to define properties about programs in my programming language. All right, so this is a K rule saying that this program, which is symbolic, symbolic really doesn't mean anything except that you have some variables in your pattern. This program rewrites to nothing. This dot K means nothing in terms of computation. The computation empties. And in the state, I start with nothing, and I have then two bindings. N is 0, and sum is the sum of numbers. Right? So it's exactly the same mechanism, reachability logic, to specify properties I want to prove about programs. And this is very important, right? Because this gives us now what we wanted, right? It gives us the possibility to define languages and write properties about any programs in any programming language in one formalism. Okay, that has never happened before. In core logic, you define your logic specific to your language. And that was critical to be able to develop this infrastructure. All right, K for the blockchain now. So what we've done, we really just instantiated this general approach with languages in the blockchain space. And the first language that we had to consider is the Ethereum virtual machine, simply because all smart contracts in the end are just EVM bytecode. So we've done exactly the same thing that we've done with other languages with EVM, where we define a complete semantics of it. It's public. It's under the LLVM. It's under the UIUC license, in case you want to use it, which is the same like MIT license, the same as the LLVM license. And we tested it thoroughly. It passes more than 60,000 tests that come with the C++ reference implementation. And that was not surprising. We did that with many other languages before. We knew that we are going to pass all the tests and that we are going to have a complete semantics. What was surprising, though, was that the interpreter that we generated completely automatically from the semantics was only 8 times slower than the actual C++ implementation of the EVM. Right? So less than an order of magnitude slower. And actually, we know how to make it faster. Now it's actually only like 5 times faster. And we want to get to a point where it will be as fast as the interpreter that you write by hand. Right? So it's getting to a point where you may wonder, why should I write an ad hoc interpreter then, instead of just generating it automatically, correct by construction from a specification? And I think that's the right question, and I think that's how we should do things, actually. And we had discussions with the Ethereum Foundation. We are in discussions with them, and there is a strong sense now of adopting this formal semantics as the standard canonical specification of the EVM to replace the yellow paper, simply because yellow paper is not maintained. Nobody spends time to maintain it, while this is maintained because there is a lot of incentives to maintain it, because all the tools build automatically from the semantics. Right? So everybody wants the semantics to be in a good shape. So what can you do with the semantics? What do we do right now with the semantics? So the first thing is that we generate a formal documentation, and that should not be underappreciated. The importance of a formal documentation is huge. So we generate a complete website called the yellowpaper.org. If you go to yellowpaper.org, you actually find a human-readable, completely automatically generated yellow paper, if you want, which is generated from the actual semantics of the EVM. Right? And it has text, and then it has rules like this. After a while, like an hour or so of training, you'll be able to read these rules. And there are several people who had not formal training who started to implement tools based on these semantics. By just looking at the semantics and implementing their tools, only getting inspiration and understanding from the formal semantics. Another thing you can do with it, besides the documentation, is to generate an actual client, EVM client. We generate the entire client from the formal semantics. And we have done that with funding from IOHK in the context of the Cardano blockchain. They actually had a test net. They started a test net based entirely on KEVM. And the entire client was generated automatically from the semantics. And the fact that it was 8 times slower was never perceived as an issue, because achieving consensus takes a lot longer than running these smart contracts. And another and the most important for my company thing that we do is to do actually formal verification based on the exact same semantics that is thoroughly tested. Right? There is no gap whatsoever between what you run and what you use for program verification. No gap that needs to be maintained. We offer these services, formal verification of contracts in my company. I also got actually the first security grant from the Ethereum Foundation to verify the Casper FFG, which was written as a smart contract. Yeah, so we verified it using the actual semantics. When you verify programs, so many people skip the part which is actually, many people claim that their smart contract has been formally verified, but what that really means is that they did some symbolic execution and they looked for some trivial properties like division by zero, overflows, and so on, very language-specific properties. But where you spend most of the time when you do actual formal verification and thorough formal verification is to write down specifications. Again, I think the blockchain is a very fortunate domain because many smart contracts are just templates. They are very simple. They implement very clear templates with very small variations here and there, which was great because that allowed us to formalize these templates once and for all and then reuse them to verify smart contracts across the board. In particular, we formalized ERC20, ERC777, some multisigs, and many other templates. We call them templates because they are really not that difficult. And we formalized all this in a language-independent way, so now you can use the same specifications to verify programs in Solidity or Viper or EVM or WASM in the future. You can just use the same specifications. Right. So this is the flow, how we verify things. So first, the first part, which is by far the hardest, and again, many people just omit that, to formally specify the requirements. That's a lot harder than the actual verification of the requirements. Right? I cannot emphasize that enough. So we have to read all these text, like this is part, snippet from the ERC20 description, and then we have to formalize it, right? We come up with rules like this. These are K rules in a slightly sugared notation. This is the semantics of transfer. What you do, you take an account, another account, from, to, perform the transfer, check some conditions, right? So you have to come up with the specifications, and then from this high-level specification, we have to generate low-level specifications that refer to the actual bytecode. And this process, unfortunately, requires some manual work. It's not entirely automatic, but we hope to automate it eventually. So you only have to write the high-level abstract specifications. All right, so that's what you can do with the formal semantics, right? So all these tools that I mentioned, all from just one formal semantics and using the generic framework. But what's really exciting is that this allows us to design new languages, and maybe better than the existing languages. Many people actually dislike EVM. Once you do formal verification, actually you immediately see lots of problems with EVM that would be so nice not to have. Actually, this is how a program looks in EVM. This is the sum program that I showed in kernel C, from 1 to something, right? It's human unreadable. You cannot understand this. Right? And yet you have to trust it, right? Because you bet your money on it. When you call into these contracts, that's what you execute. Why should you trust this code? Well, there are reasons why it needs to be low level, but I would like to write smart contracts like this. This is LLVM, basically, more or less. And we designed an LLVM-like language for the blockchain, which we call YELE, again in a contract with IOHK, where they said, okay guys, so you verify lots of programs with EVM, what would be a better EVM? I said, well, better EVM would be LLVM, in my view. And then we started designing LLVM to run blockchain contracts, but it turned out that LLVM had a lot of infrastructure that was completely unnecessary, And some things from EVM were actually good and wanted to have in the language. So we designed, in the end, an LLVM-like language, which is ELE, and also implemented a compiler from Solidity to ELE, so you can run legacy contracts on the new blockchain. We're also working under various projects on several other languages for the blockchain, like we are formally defining the semantics of WASM, Solidity, Plutus, Viper, as we speak. K actually is more general than just defining semantics of languages. You can define semantics for anything, basically, including protocols. I mean, I showed you already how you can define semantics of ERC20 or token specifications. You can just as well define protocols. And we are also working on several projects mostly with the Ethereum Foundation, but also with other companies now, where we formalize the consensus protocols, and then we generate reference implementations of them from the actual semantics by simply running the K rules. So I have 5 more minutes for presentation, and then, right, okay, I'll go faster. All right. So now let me tell you a few words about the ongoing K projects, in case you are interested. You are more than welcome to contribute. We need a lot of help. So there are 3 main projects, actually 4, where we put a lot of effort into. One of them is to get faster interpreters, right? So I think we got to a point where we cannot make our OCaml-based interpreters any faster. We reached the limits of OCaml. So what we do now, we generate directly LLVM. And we already have an interpreter which is twice faster than the OCaml-based interpreters. And we don't even do garbage collection yet. We know we can make it a lot faster. So you are welcome to help. There's a lot of work going on here. The vision, the dream here would be that we can generate interpreters from formal semantics which are as fast or faster than interpreters that you would write by hand. I mean, you can always write by hand a faster interpreter, but you have to be a super expert to know exactly what you're doing, while the framework will generate pretty fast interpreters when the time comes. We'd also like to generate compilers, actually to go beyond just generating interpreters. And we have some prototypes where what we do, we use symbolic execution, which already exists in the framework. And we symbolically execute the program on all the paths that do not need runtime information, and we summarize the semantics of those and generate a new language semantics, which is specialized for your program. So you take a programming language semantics and the program, and by partially evaluating the program with the semantics, you get another semantics, which is specialized for your program, right? And now you just run it with the interpreter. And for example, this is a program in kernel C again with 2 nested while loops, and after SBC, we get this language semantics, where these are new commands in the new language, and these are the right rules, saying how you change the state, how you check additional conditions. Red means conditions, green means transitions, which is actually also what a compiler does. A compiler generates a control flow graph like this with data information, but what's interesting here is that you can generate all this completely automatically based just on the semantics of the language. You do nothing language specific, and if we can make that work, then that can be really, really big, I believe, because it can change the way we do things completely, where you do not implement compilers anymore. You generate them from the semantics. And as expected, when you compile, you see orders of magnitude performance improvements. Finally, we work with more and more companies in the blockchain space who, once we verify the contracts for them, they ask, why should we trust your K tool? Your K tool is a huge piece of code, and like any piece of code can have bugs, why should you trust it? And my answer is that you should not, but unfortunately that's all we can do right now. But since there is a uniform logic under the hood, this matching new logic, our next step is to actually generate proof objects. Everything K does, everything all these blue boxes do, is to search for a proof in matching logic. So we are going to make them spit out a proof object that then can be checked by third parties without having to trust our framework. And then you can have smart contracts verified on the blockchain, and you have a proof object that certifies the correctness of the smart contract. And you can check that independently or have a third party check it for you. And the logic, this is actually the proof system of matching logic, which is language independent. It has only 16 proof rules. The proof checker is only 200 lines of code. That's the only thing you have to trust in the end. The 200 lines of code that are public, you can re-implement the proof checker yourself in the morning if you want to, if you don't trust my implementation or whatever implementation. The point is that you reduce trust from 100,000 lines of Haskell and Java that K implements to just a few lines of proof checker. All right, and finally, let's push a bit the envelope. I like to believe that actually we can use K as a universal technology for the blockchain, not only to do verification, but actually to have a whole blockchain powered by a tool like K. Essentially, what that would mean is that your EVM or your smart contract language in the blockchain should not be EVM or LLVM or any other language. It should just be K. So what you put in the blockchain, your smart contracts are K definitions. Right? In particular, you can have all the language semantics that we have so far, like for Solidity or for Viper, different versions of the semantics. All these become smart contracts now that you can put on the blockchain. And then if you have a program, you can write smart contracts in any programming language for which you have a formal semantics, and you can SBC it. And once you SBC, do the semantic-based compilation, you get another K definition, and you put that K definition as well on the blockchain. That's your smart contract. And there is only one virtual machine now, the K virtual machine, that you run in each node. And that's all you have to worry about now. Just one VM, and then programming languages can be stored on the blockchain, and you can write smart contracts in any language, literally, and have all the tools for the language. And everything is perfect. There is no compromise in terms of correctness. And K itself can be used as a language for writing smart contracts. I don't necessarily have to only use such an infrastructure in order to write smart contracts in any programming language. I can write my smart contracts directly in K, because K is not as bad as a language for writing programs in it. For example, this is a snippet of ERC20, and this is what you get once you compile it with a Solidity compiler. And obviously, this is human unreadable. If you try to make some sense of it, you decode it into opcodes, like push, pop, and so on, still human unreadable. And you have to trust this. So this is unreadable. It's slow. Actually, it takes 25 milliseconds to execute the transfer function on average on a particular computer. But what's really critical here is that the compiler is completely untrusted. Right? Actually, we do not verify Solidity code. We only verify bytecode simply because we do not trust the Solidity compiler. We found countless bugs, countless numbers of bugs in the Solidity compiler. So you should not trust the Solidity compiler if you really are serious about correctness. But in order to verify this code, in order to trust it, you need to write specifications. And this is the case specification of the transfer function. Okay? I guess you agree with me that it is not that unreadable, right? It's saying that the transfer is true. You have the caller from, you go to the account of from, decrement the balance, increment the balance of the receiver, you log the event, and you have some additional conditions that you check. And actually, if we execute this specification, it's executable. So I use it to prove the correctness of the smart contracts, but it's also executable. And ironically, it's not only formal, but if I execute it, it's only 2 milliseconds. So it's 10 times faster than the EVM code. So why should I even write smart contracts in EVM or Solidity, for that matter? And this is all correct by construction, and there's no compiler required. I'm done. Thank you. I actually firmly believe that we can do this. K may not be the final answer, but I think it brings enough evidence that, that this is possible.
Thank you very much. It's very early. I would try to keep the program without major delays. We have 5-6 minutes for questions. You can.
Yes, you're first.
I would like to ask about the K language. Could you tell some word about decidability of the K language? Because you say you have a precondition, and in this language you have the rules, and you implement the symbolic modeling and different other program. So What kind of logic or how you can characterize the decidability of the formulas in this
Nothing is
case?
decidable. Nothing is decidable. We have a relative completeness theorem, same like in Hor logic, which says that if you have an oracle for deciding your domain constraints, like SMT solvers, like Z3, for example, we use all those as an oracle. So what the relative completeness theorem says that if you have an oracle that can decide truth in a current state, then the proof system of matching logic is complete. Then you can prove any property about any program, provided you have an oracle about the assertion language, which is the same result that you have for Hor logics, but it's language parametric now. It works for all languages.
Then could you please you didn't mention what kind of properties you verify in a K program?
So there are two aspects here. There is the logic, matching mu logic, which allows you to express properties in any of those logics that I mentioned before, temporal, first order, inductive properties over first order logic. So it's very expressive. And now there is what we implemented in K. In K, we implemented a fragment, which is only the reachability logic, which means that you start in this state and you reach a certain other states. And we have two variants, on one path or on all paths.
So the reachability problem is undecidable in general
Yes,
way.
it is undecidable. Yeah.
Yes, and one more question.
Yes.
You said that your...
It's also human interactive. You have to help it.
Yeah, okay, yes.
Yeah, yeah.
And one more question, and so you talk about the high level of the language. What to do with the uncompiled component, I mean library and system calls, and this is the main
Right,
source
so-
of cyber,
Yeah.
of exploits and vulnerability.
Yes. So for execution, the interpreter just calls those functions natively. We have an interface how to call natively libraries or any native code. But for verification, you need to formalize the semantics of those if you want to reason about them.
It's too many libraries.
We have a semantics of x86 now. In principle, you can use that to verify, but I wouldn't go that path.
Okay, and last question. Do you satisfy that 3 Microsoft prover?
What is that?
Do you satisfy of this Z3 Microsoft proven machine?
I'm happy with it.
Really? Okay. thank you.
But Nikolai Björner is a good friend, so whenever I have a
Yes,
problem, I
yes,
complain,
know,
and
but it's too
and he
slow.
fixes it.
It's too slow, and if you
It is
have
too slow, but let me tell you something in K different from Hor logic. In Hor logic, when you do verification based on weakest precondition, you generate these huge formulae, and then you send them to Z3 and basically pray. You hope that Z3 will terminate. So what we do in K, we do executions, small step executions, and we have lots, thousands, tens of thousands of calls to Z3, but with much smaller formulae. So we have a better success with Z3 than Hor logic-based verifiers.
Thank you.
Hi.
Question for another question, but like 2 minutes.
Okay. Yeah. So my question is really short. Basically, just I guess one reason why you wouldn't want to use K as the actual language on the blockchain is that I guess the running time of compiling the K program is unbounded, and you never want that as a DDoS vector on a blockchain.
Yes, that is a problem.
That's why blockchains typically use a very low-level language where you can prove the runtime of the program.
Right, right. But there is nothing to stop you from compiling the K contracts into LLVM, let's say, right, and then keep the LLVM bitcode.
Yeah, and I guess another reason why they use EVM instead of LLVM is also because LLVM has so many complex constructs that may take unbounded
Yeah, you
time.
can keep a fragment, take a fragment,
Yeah.
like the Yele fragment. That's what we try to do with Yele.
Okay.
Take a good fragment. But you are right, I agree, that is a problem. And then gas metering is another issue. You would have to charge gas for matching a pattern.
Yeah, so like
which is
basically
not trivial.
what I was referring to is that I think the idea that you can have smart contracts in the blockchain that you can read in a human readable way on the blockchain is sort of elusive because of this problem. You have to use a really low level language.
Well, we can talk about that.
Okay.
Hi.
Yes.
Isaac Chef, Cornell. I think this is a really exciting body of work, but I wanted to ask, you mentioned that the proof search could be interactive, that you could help the compiler
Yes.
look for. What does that look like? What do those
You have to
human
write. You have to write like invariants, but we don't have a notion of invariant. But you still have to write like a lemma, capturing the property of the while loop, and then you can use it in the bigger proof. Even the little program that I showed before, the sum of numbers up to 10, right, has a loop inside. So to prove that program, you need a loop invariant, which I didn't show, but there is no other way. right, to prove it. So you see, you can execute this symbolically, no problem, but then you hit the loop. And if you keep going into the loop, if the loop has a bounded number of iterations, then you can simply execute it and finish and prove the program. But if it's like here, which is unbounded, or it depends on some symbolic value, the number of iterations, then you need a lemma, which is another reachability rule, capturing the semantics of the while loop. And then you have to there is a co-inductive proof principle, actually, where you have to use the semantics of the while loop in order to prove it itself, right? So I have to unroll the while loop and then prove that whatever I claimed about the while loop is stable.
Thank you.
Okay. There's in the back. Your back.
Yeah, so just a question about expressiveness. Once you get into much richer types of properties like ATL or monadic second order logic, or do you want to do probabilistic reasoning, or sort of Black-Scholes type valuation on financial contracts?
Right, right.
Are you rich enough to handle any of those?
So I think that's a long discussion. For example, we managed to define hyper properties, which we thought we couldn't define. Basic properties over multiple traces, not just one trace. For probabilities, what we do, or for to measure, like to have other resources like time, how long it takes to do something. What we do, we play a game between methodologies in the logic, how to define things, and changing the semantics of the language, where we keep track of more information, like how long it took to execute the program so far. Right, so we can add a new semantic cell and then meter basically the execution of the program. Or if you have probabilities, then you can have a probability for each semantic rule, and then when you execute the program, you can update the probability to be there basically as you execute the program. And then of course you also need specification mechanism for probabilities in the formulae. But so we have not done it. But typically when we need new features, we play this game between defining things in the logic, new theories in the logic, and modifying the semantics of the language to keep track of more information that I need in order to express my properties. So it's basically first order logic and induction. That's the expressiveness of the first order logic with induction. That's the expressiveness of the logic right now. All right.
Great talk, Grigore. Now, these days, open source is a good thing and trend, and I wonder. I know you're doing a company, commercial company, and but many commercial companies do this. Provide simple version open source or freely available, especially for academics. Do you have plan to do that, or are you already doing that?
So currently, everything we have is open source, but we already started working on parallel versions of our proof searchers, and then want to offer those as a service, software as a service. So basically, it's a free version of the tool that you can use for free, but you have to wait 2 hours for a proof to be done, or you can pay a bit, and you can have the proof done in 5 seconds.
So you have freely available version already?
Everything is free right now.
On the internet?
Yes, yeah.
Is it available on your slide?
Yeah, kframework.org, and then you can reach everything from there.
Great.
Yeah.
Excellent.
And it's under the UIUC license, which is as permissive as the MIT license.
So let's thank one more time our keynote today for coming and for this beautiful and very interesting talk.
Thank you. Thank you for the great questions.